Alright, hell yeah. So this is part 6, dynamics, doing differentiation. You know, and part 5 was rough, but we did a kind of a harder method. And so we're going to try to do not the most textbook way, but just kind of, well, this would be the textbook way. It's not like the pro way that I would do it. But hell yeah, it all comes down to the setup. So here is the center of the circle. So obviously this is the radius. This is the point O of where the pivot is. So this is where this circle is kind of lopsidedly spinning. This actuator goes up and down. Hell yeah. And we have some continuity here. Like, why do we even need to know this angle? It's because we need to know this total distance right here. You know what I mean? And I'm just going to call this y. And the only way to get this distance y is be like, well, I know this distance here and I know this distance here. You know what I mean? It would be like, hey, I'm going to walk this way across the park and that way across the park. Well, if I know this direction that I'm walking to the park and then I know this direction that I'm walking, well, hell yeah, I know exactly how far I walk this way and that way. So that's kind of in a nutshell that we need this length. And this length is changing. Let's break out this cool demonstration. So this is the actuator. This is life size of what's happening. When it's totally vertical, the actuator is up there at that green one. At a 45-degree angle, you get down to here. And then as this thing spins, the actuator, you know, just imagine the green thing is the actuator going up and down. And then the actuator goes all the way up there. I guess they call it a follower. But anyway. And so that's that. So we're going to do some differentiation. Or why did I say that? Is like, because we need to know this height, and then we need to take the derivative of it. If we change this height with respect to time, we'll know the velocity. You know what I mean? If this is the height, that's all we know. But if we change time by like a second, and the actuator goes down there, hell yeah, we know the change in position, and we know the change in time. That's the definition of velocity. Change in this case, change in y. Change in t. Cool. All right. So if we know that this is the hypotenuse and we know that this is the angle, we're going to say that this is E sine theta. All right. Sorry about that. So we have the angle. The sun is shining on the sine component of the hypotenuse. Sines and cosines are percentages. Sine is a percentage of the hypotenuse in this across direction. This is the adjacent direction. This is going to be E cosine theta. This we don't have to do because we already know that this length is E sine theta. And we want everything in terms of theta. Theta is kind of what we're measuring, and then we want to know the velocity of A. But the only... but we will do this. We'll say R sine phi, because in this problem, we want to know, and then this one, we're going to do R cosine phi. This is how we set up part 5, and we said that y is equal to R cosine phi plus E cosine theta. And we took the differential of this with respect to time. You do a chain rule, so you got to differentiate this with respect to phi. That's going to give you a phi dot, because you would have d of this d phi, but then d phi dt. Basically, derivative of this, but then a phi dot. So we don't want that. We just want, right now, we want an equation for phi as a function of theta and throw it in right now. So that's what we're going to do. And then differentiate. So we're going to see that these two are equal, and we're going to, we did this in part 5, and then we're just going to solve for phi. So we're going to kick this r over there, and then we're going to take the inverse sine of this. So sorry, a little sloppy, but there you go. So this is phi. Phi is equal to the inverse sine of E divided by R phi. I'll write it one more time. Phi is inverse sine E divided by R sine. See, and I got all mixed up. Sine theta. Holy hell. I think I really messed up. So we're going to do... I think I should have said this is theta, but I'm just going to double check. If these are equal, and I want to get it in terms of phi, I'm going to say phi is equal to E divided by R. So we're going to get the R to the other side and then inverse sine that. Inverse sine E divided by R sine theta. Whew. Yeah, I just had that. That was the only mistake. Sorry for crossing all that out just for that. Okay, so let's get our original equation. Y is going to be R cosine, and now we have cosine of inverse sine e to the R sine theta. All right, hell yeah. So that looks like a royal mess. You know what I mean? So we're gonna see if we can do something with that. But such is life. And then we're gonna do e cosine theta. Now this is gonna be cool, because I thought I was trying to do this in the other video. So we're going to do just a generic triangle. And we're going to say, here's our angle theta. Everything's in theta now. We're going to say the inverse sine, this is a ratio. Anytime you're taking an inverse sine, this must be a ratio. And this ratio, if it's inverse sine, must be the opposite over the hypotenuse. So we can actually put ER sine theta here, because all you have to do is just take this, divide by 1. So the hypotenuse is 1, and then we know that. And then so this is the magic, because don't we take a cosine here? And what's cosine? Cosine says cosine, oh yeah, cosine of an angle. You know what I mean? So if we have an angle right here, this now is an angle of this triangle. But if we have an angle and take the cosine of it, that's going to be the ratio of the adjacent over the hypotenuse. You know what I mean? So we're still dealing with the same triangle. So we have this ratio divided by 1 is this triangle. We're taking the inverse sine of it. I mean, basically, you're saying that this is what we're finding, this angle of this triangle. Cool. And then if it's the same triangle we're putting in here with that angle, and we're taking the cosine of that triangle, well, now we're just trying to find this adjacent over 1. And so, hell yeah. So now I'm really excited, because this is what we were trying to do in the other video. And I'll spell it out, because we have Pythagorean's theorem that's a squared plus b squared is equal to c squared. You know what I mean? We have a hypotenuse, that's c, a and b. And to solve for c, we just take the square root of that. So I think you've seen that quite often. But if we want a squared plus b squared plus c squared and solve for like b or a, let's solve for b. We do this. B squared is equal to, whoops, this is equals. C, but we got to subtract a squared and then maybe take the square root of it. Okay, hell yeah. And so the thing that you can just do to memorize it is just like, hey, I want to know what this side is of this triangle, right triangle. I'm going to say 1 squared, but I'm going to go minus. If it's these two sides squared add, and the square root of both these sides additive equal the hypotenuse. Hypotenuse is always the bigger number. So if we're starting with the hypotenuse, even if we're squaring it, hell yeah, we have to subtract, you know, this squared. And so instead of doing like this squared, I'm going to go e squared r squared sine squared theta. That's the same thing as squaring this whole thing. Okay, and now we're going to take the square root of it. So hell yeah. So this just becomes 1 minus e squared divided by r squared sine squared theta. Sine theta squared. Okay, so now we're going to take the cosine of this triangle. So this triangle has a hypotenuse of 1. This side is what it is. This side is what it is. So the cosine is the adjacent over the hypotenuse. So it's just this. This is the definition of cosine of that angle. Sweet. So we're going to have, so for this y equation, we're going to have r. And then for this, hell yeah, let's get rid of the square root across. We're just going to bracket it in, and we're going to raise it to the half power. So we're going to 1 minus e squared r squared. And man, do I dare? Yes, I do dare. So we're gonna when differentiating, I think it makes your life easier. Anything downstairs, just kick upstairs, even these constants. So we're going to go, and this is the other thing we're going to do. We're going to take a pause. So we're going to say y. This is all the strategies that I use. All right, sorry if the camera was so dark. I just lightened it. But anyway, so here's the strategies that I use. We're going to say, like, where are we at on this? Right here. So we're going to say this cosine thing is just that. Sorry, it's just so close to this equation. But we're going to do this. We're going to say r, bracket this in, 1. Instead of minus, I'm going to do plus, but I'm going to do a negative 1. Just because we might have other negatives along the way when we do the integration or the differentiation process. I'm going to go e to the 2, but I'm going to go r to the negative 2. Hell yeah. Now, I think I'll probably develop a better strategy of even bracketing that in, just so I'm like, oh, heads up, it's a negative. But anyway, we'll just keep that for now. And then sine squared theta. Because if sine squared was downstairs, I could just do a negative 2 right here. And then we're going to bracket that all in and take it to, and then I do this, 0.5. I'm using decimals, not fractions, when I'm doing this. Because then when I subtract 1, it's just really easy to go to negative 0.5 and then negative 1.5, taking further derivations. All right, hell yeah. So that's that, and we're done. And then we got this part 2. We got plus e cosine theta. Okay, hell yeah. So now let the work begin. And maybe we could squeeze it in to this. Probably not, but we're going to differentiate with respect to time. And then that's this side with respect to time. I don't see time here. I see theta here. So we're going to do the chain rule. We're going to differentiate all this jazz with respect to theta. But then make sure after we get all that craziness, we're going to do this. D theta dt. And these will cancel. In theory, they cancel. They kind of, just right now in theory they cancel. But this becomes theta dot. So we just, after differentiating, we just got to make sure we add a theta dot. All right, hell yeah. And we're going to give ourselves a lot of paper. So heck yeah, let the differentiation begin. We're going to differentiate both sides with respect to time. Obviously, it's differentiating with respect to theta, but let's begin the process. So r is a constant, and so we can just like put it outside. But anyway, but we have this. We have this whole square root thing. So we need to bring down the power. So we're going to have r 0.5. Oh man, sometimes I bring down I usually don't do it like that at all. Sorry about this. So my bad. We're going to do r. I just have to do it in ways that I enjoy and just make my brain not hurt. So I'm going to bring down that half and write it like this. Because hopefully we'll probably have a 2 here. They're going to cancel anyway. Because I've done some of these problems before. Anyway, so the power comes down. Everything inside stays the same. 1 plus. So it's just a lot of, rewriting things too. Okay, and then the power goes to the negative 0.5. And then we have to differentiating what's in here. Now this 1, that goes to 0. All this is a constant. So keep that in mind. But we're going to get the constant, just, get that outside. So we're going to do the constant first. And then we're going to differentiate this. Now just remember, this is sine theta squared, so we can bring down the square, bring down the power, and then and then we'll have sine theta. So we brought down the 2, and then this goes to 1, or just 2 times sine theta. Then we have to take the derivative of the inside. That's going to be cosine theta. Hell yeah! And now we're done, but now we have to just make sure to put that theta dot. Okay, and now we're going to do this. This is going to be, we have a constant e, we have a negative 1, because, I should have done this. So cosine graph goes like this, sine graph goes like this. Sine graph has a slope of 1 at 0, so cosine of 0 is 1. So sine goes to cosine, but this has a negative slope. So just know that cosine goes to a sine because the slope is 0 here at 0. Sine of 0 is 0, but it's a negative slope. It starts to go. It's always negative, so it's going to be negative sine. So we have this derivative of cosine is going to be negative 1 sine theta. Hell yeah. And then theta dot. All right, booyah. So that is done. We have our velocity, and I'm sorry I just wrote it like that, but we could probably, anything we can simplify. We have a 2 here and a half here. Cool, cool. And then we have an r here and then an r downstairs. So this will be r to the 1. Okay, hell yeah. So I'm just going to go, we're going to get rid of that one. And this goes r to the negative 1. Anything else? That's about it. We do have to keep this negative 1. So cool. So we're going to do negative 1 e squared r to the negative 1. See how many errors I could probably, pick up, even just trying to simplify this stuff? Okay, hell yeah. So this square root really doesn't change, but it's a downstairs square root. 1 plus negative 1 e squared r to the negative 2 sine squared theta to the negative 0.5 multiplied by sine theta cosine theta theta dot. Remember, this is just the angular velocity, and that's given. This whole thing's just on a motor. It's going at a constant speed. It's going hella fast, 17 times per second in revolutions, 1,000 revolutions per minute. Cool. So, and then this one's just going to be plus. I'm still going to write it negative 1 e sine theta theta dot. Now the moment of truth. We should be able to put this in my calculator. I feel like I've made one error, but I don't know. I'm about, I don't know, we'll see. Alright, hell yeah. So I'm just going to check my calculator. Alpha r is 100, alpha e is 60, alpha theta is 60. Because that's the problem statement. It's like, hey, find the velocity of this follower when this angle goes all the way to 60. What's the velocity of this? And again, like, let's not forget, we need to find the height. We need to find the height at any given angle. You know what I mean? So I think we could do that. You could come up with an equation to find this height given any input of the angle. You know what I mean? That's the first thing that we did. And, y is equal to this, or y is equal to that. Yeah, we got that. Y was equal to that. And then we figured, yeah, we got this, and then we kind of simplified it. But this was our height given any angle. All we got to do is pop in an angle, and we get a height. But that's only one step of the game, because we want to go at the height around 60, and then we want to vary that angle, to 61 or 59, 59 to 60, 60 to 61, and see how much that distance changes, and just know. So does that make sense? We want to change this distance y while we're changing theta, and we know that a change in theta is related to a change in time, and then we're going to take change in y, change in time to get velocity. And literally that is exactly what the chain rule is. We're going to take the change in y. We want change in y, change in t. Can't have it right away. But we can have is change in y, change in the angle. That is literally the definition of the, we're using all those rules that apply of how to find a differential equation. But we need to take this change in angle and associate it with a time. You know what I mean? We basically need to turn this into a change in time and put it downstairs. We do that by multiplying by the angular velocity, change in time, change in angle per time. This is theta dot. And when we do this, we do get the change in time downstairs. All right, hell yeah. And so if you did this in separately, I would say, hey, maybe my change in angle is like 1 degree. So cool, we got like 1 degree, or like 1/6 a radian. No, that's not right at all. 1/30th. 1/30th divided by 1/6. Yeah, holy hell. I'm losing it. But anyway, you would find the change in angle, and then you would take that change in angle and you would divide it by the angular speed. So let's say we found the change in angle in radians, and then you would divide it by the angular speed in radians per second. Seconds would pop upstairs. This would give you that change in time. You would take that and then divide it by that change in position. So you're doing that process like kind of an upstairs way. Change in theta is upstairs divided by angular speed. But here you're doing it in a downstairs way. We know that differentiating this equation gives us this, and so then you have to multiply it by the angular speed, and then you get that change in y, change in t. Alright, booyah. So moment of truth, let's throw this into our calculator. So we got bracket -1 alpha e squared alpha r to the -1. Looking good so far. 1 plus -1 alpha e squared alpha r to the -2 sine theta squared. Alright, so all that is going to be to the -0.5. You know what I mean? So cool. Sine theta, cosine theta. Theta dot in my calculator is omega, or w. I didn't show you that. But now we're on to the next term. Plus -1 alpha. Oh, don't need parentheses. Sine theta and then omega. Alright, hell yeah. So I'm feeling really confident and overconfident now because I made a hell of a lot of mistakes trying to learn some of these processes, and just learning to not make mistakes, or like, you know, seeing where I would make mistakes, and then doing things like these. Like, I hate negatives, you know what I mean? They're going to mess me up. So even right here, I think I'm going to go to the process of being like, hey, I'm going to call that r to the -2. It's just going to jump. Well, I don't know. I can see it. Because I'm not gonna do this. I'm not gonna go sine to the -5 and then bracket it in. I might at some point, but currently, you know, that's what I'm gonna do. And I can pick up on. I can kind of see the negatives. But at least just having everything upstairs will make your differential life a lot easier. Here we didn't really have multiple terms. Like, we had things that were sandwiched, but we didn't have a product. We didn't have this square root multiplied by another square root or something, you know. Even when we had the sine squared, that is a product of sine and sine times sine, you know. So let's end the video with that. If we have sine theta, and we're taking the derivative of it, we're going to have the first times the derivative of the second. That's cosine theta. Plus the second times the derivative of the first. Cool. And it'd be like, whoa, we have a lot of terms. But no, this is, again, I made a video on this of just like, I did like 4 square roots of 3 plus the square root of 3 is the same thing as saying 4 square roots of 3 plus 1 square root of 3. And it's like saying 4 apples plus 1 apple. Cool, we got 5 apples. You know what I mean? We got 5 funkies, you know, so we got 2 funkies. So we got 2 sine theta, cosine theta. And hell yeah. So that's like, even something like that can confuse me. In 20 years from now, that's going to confuse me. But hell yeah. So 2 sine theta. So now let's figure out why we did it the way we did it. So we're going to have sine theta squared. We're going to take the derivative of this with respect to theta. Bring down the 2. So 2 pops out. The thing inside stays the same. The power goes from 2 to 1. So we could put the power right there. And then you got to take the derivative of the inside. That's going to be cosine theta. Oh, and look at that. 2 sine theta, cosine theta. So this is called U substitution. You take du, du, and this is going to, du dx. I mean, yeah, I don't know. Yeah. D, whatever the variable is inside, but just for the time being, and then du dx. And anyway, yeah, I think you get it. U substitution, whatever. But that's the reason you didn't have to do any products. So we just kind of let that nesting, I need to stop stuttering. That nesting allows you to do that differential process. I don't know, just pretty nice. This one, yeah, it wasn't 9 terms. Some of these you have to, like, you know, if you have 3 different products of 3 different things, you're gonna have to take the first times the derivative of the second. You know, the first and second times the derivative of the third. That's one thing. Plus, the first and third times the derivative of the second. That's another thing. Plus, the second and third times the derivative of the first. I mean, basically, you take this derivative, but you still got to multiply it by the remainder. This derivative multiplied by the remainder. Then this derivative multiplied by the remainder. And then you got 3 terms. And if you already had this, you know what I mean? There's going to be 6 terms, and life is absolute madness. And then you take the next differential, and it's just going to multiply it. So it's awfulness, and there's just a lot of places for error. So hell yeah, we did pretty good on this one, and I'm just, I don't know if I'm done with this series, but we did pretty good with the actuator. Pretty cool. Alright, hell yeah, that's the video.